Okay, so in this final video, we will talk about viscosity. Okay, viscosity is a fluid's ability to resist flow. Okay, it's like the resistance of the fluid to resist flow. Okay, so for example, you say that okay, water flows very freely. So you say that water has a very low viscosity because water is not sticky at all. But then you say, oh, the honey flows very slowly, and then you say that honey is very sticky because honey has a higher viscosity. Okay, so actually there are three factors affecting the value of viscosity of a certain fluid. Okay, for example, the first one is the size and shape of the molecules. Okay, so you know that the water molecules are obviously more simpler than the honey molecules, okay, which are glucose molecules. Okay, so since the H2O is a tiny molecule, therefore those H2O molecules can move past each other more easily. Okay, but then for such a complex and such a heavy molecule, they are harder to move freely. Okay, so when the size of the molecules increases, viscosity increases. Okay, or maybe you say that the more complex a certain molecule, the higher the viscosity of that liquid is. Okay, the second factor is the strength of the intermolecular forces. Okay, so for example, you know that in water you have what? You have your very strong hydrogen bonding because of the oxygen atom is more electronegative compared to the hydrogen atom. So when you have a partial positive charge here and then you have a partial negative charge here, there will be a force of attraction. Then this force of attraction is known as the hydrogen bonding. However, for the honey, you only have van der Waals forces, okay? But then because the molecules are very complex, so the heavier the molecules, the stronger the van der Waals forces will be. Okay, and then the third factor is the temperature. Okay, when you increase the temperature, the molecules get more energetic, and therefore since they are more energetic, then they can flow more easily. Okay, then you say that the viscosity decreases. Okay, so you know that among these three factors, the dominant factor that determines that the water has a lower viscosity than honey is the size and shape of the molecules. Okay, because since this factor is more dominant, then you know that the honey is more stickier, okay, than water. So honey has a higher viscosity compared to water. So please differentiate between viscous forces and frictional forces. Okay, you know that when you study frictional forces, we always say that when two surfaces are in contact, then there must be some frictional forces. Okay, I don't care whether that's kinetic frictional forces or static frictional forces. As long as there are two surfaces in contact, I don't really care about the motion. I don't really care about the movement. There must be some frictional forces. Okay. However, for viscous forces, these type of forces can only exist when there is some flow of liquid. If the fluid is static, okay, that means that if the fluid is not moving at all, then you don't have viscous force. Okay, so now assume that you have two plates, okay, two parallel plates, and then in between the plates you have some slab of water, and then the viscosity of the water is eta. Okay, so this plate, this lower plate is fixed. Okay, it's fixed in place, you cannot move it. But then now you can pull this plate such that it moves at a velocity v. And then now this is your water, right? You know that actually the water molecules at this level have the exactly same velocity v as this plate, okay, because they are at the same level. Okay, and then the water molecules here move slightly slower than here. Okay, that means that here moves very fast, and then here slower, and then here slower, and then here much slower, and then finally the velocity here is 0 because you know that the plate is fixed. Okay, actually this is known as the momentum diffusion. Okay, for example, if you say that here is very hot and then here is very cold, then you know that here is slightly warm, this is colder, this is even colder, this is coldest, this is hottest. Okay, and then yeah, for example, if you say here has a high concentration of sugar solution and then here is pure water, then you know that the concentration of the sugar here is the highest, and then lower here, and then even lower here, and then lowest here. Okay, so this is like diffusion process. Okay, and then this is actually the velocity gradient. You say that the velocity here is very large, here becomes smaller, even smaller, very super smaller, and then lowest. Okay, so please find the expression of force needed to pull the upper plate such that it can move at a certain velocity v. Okay, so you say that if you want to move it faster, then of course you need a greater force. So force is directly proportional to velocity. If the water is more stickier, okay, you will need a greater amount of force because the water is more stickier, so it wastes a lot of your energy. Okay, because it opposes your motion. Okay, so F is directly proportional to viscosity, and then the area is the surface area of the plate here. The larger the area, the more water molecules in contact with your plate, so the more water molecules you will need to waste your energy on. Okay, so that the greater the area, the greater the force needed. And then if the slab of the water gets thicker, that means that you have a very thick layer of water here. That means that when L increases, the force actually decreases. Okay, just take it that when you have a very thick layer of water, it becomes mover. Okay, but then when the water is very thin, it is not that smooth. Okay, so you know that F is inversely proportional to L. And then okay, from here, right, we straight away jump to the formula. And then I should be very honest with you, because actually we should use Newton's law of viscosity to derive the formula, but then unfortunately I've not learned that yet. So yeah, but then that is not the point of the story, because I just want you to know that the force is directly proportional to eta and also the velocity, because later on we will have another Stokes law. And then for the Stokes law, right, Stokes law, we also say that the force is directly proportional to eta and v. Okay, so let's now use this formula to answer a few questions first. Determine the force that needs to be applied in order to pull a microscope slide over another at a speed of 1 × 10⁻⁻² meter per second if there is a 0.3 millimeter thick layer of water between the slides. Assume the viscosity of water as 1 × 10⁻³ Newton second per meter, and then the surface area of the slides is 10 cm square. Okay, you use the formula. A block of ice of surface area 0.3 meter square is drawn over a 0.2 millimeter thick layer of water. Please find the force needed to pull the ice block at a speed of 0.3 meter per second. Take viscosity as 1.792 × 10⁻³ Newton second per meter square. Okay, so yeah, by the same reasoning, you use the same formula. Okay. Okay, now we have to deal with Stokes law. Actually, this law is only applicable for a spherical object. Okay, so if you are using a rectangular object or maybe a triangular object, then Stokes law is not applicable anymore. Okay, so now you assume that a sphere is sinking in a fluid. Okay, so the drag force, okay, the viscous force that retards a sphere moving through the viscous fluid is directly proportional to the velocity and the radius of the sphere and the viscosity of fluid. Okay, so F is directly proportional to R. Okay, because you know that the greater the R, the larger the sphere. So when the body gets larger, of course it can experience a larger viscous force, okay, because it will experience more frictional force. Okay, so F is directly proportional to eta. Okay, the stickier the fluid, of course the viscous force will be much greater, right? Okay, and then if the sphere is moving at a higher velocity, then it will experience a higher drag force. Okay, just like when you are not moving, you do not feel frictional force from the air molecules. But when you are driving, you can feel that a very huge resistance from the air molecules. Okay, when the air molecules can make your hair fly, yeah, something like that. So you know that the greater the velocity, the greater the drag force. Okay, and then what do you do now? You use your dimensional analysis to find the power of R, eta, and also V. Okay, and then K is a constant of proportionality. Okay, and then for this constant, right, you only have some numerical value, and then normally the numerical value is obtained from your experiments, and then you don't have any dimension for this constant. Okay, so yeah, you do your dimensional analysis. Okay, for example, you say that F equal to ma, and then you say, oh, units of the force is kilogram meter per second. So you say that the dimension is mass, length, time, -2. Okay, radius, you use meter, right? So the dimension is L, length. Okay, the velocity, meter per second. So you say that the dimension of the velocity is length per time. Okay, just now you use this formula, right? So you find out the dimension of eta. The viscosity has a unit of kilogram per meter per second. So the dimension is mass per length per time. Okay, so you use your powerful mathematical skills to give me the power. Okay, I want to find out A, B, and C. Okay, so you check for mass, right? The power is 1 here, and then here is B, so you know that B equal to 1. For the time here, this is -2, and then this is -B, -C. Just now you know that B equal to 1, so now you know that C equal to 1. And then finally you check L, okay, and then you can get A equal to 1. So you know that A, B, C, they are all 1. Okay, so from your experiments, you know that the constant here is 6 pi. So you say F equal to 6 pi R eta V. And then this is the drag force or the viscous force for a sphere. And then this is known as Stokes Law. And then we will use this Stokes Law to find out the expression for the terminal velocity of a spherical object moving through a fluid. For example, let's take a look at this question here. Okay, so you have to use Stokes law, the expression for the viscous force, in order to give me the expression of the terminal velocity of a spherical object, okay, moving in the fluid. Okay, so let's take a look at this. A copper ball of radius 3 mm is released from rest into a large cylindrical container filled with glycerin. Determine the terminal velocity of the ball by taking the density of the copper as this one, the density of glycerin at this one, and the viscosity of the glycerin as this one. Okay, so now you say when the ball reaches a terminal velocity, right? You say that it has no acceleration. Therefore, the ball experiences zero net force. Okay, so you say that the force in the upward direction is exactly the same as the force in the downward direction. Okay, so when the ball is moving downward at a constant velocity, which is the terminal velocity v, okay, it can experience three types of forces. First and foremost, when you have mass, you have your weight. When you are in the fluid, you know, from Archimedes' principle, you have a buoyant force. And then when you are moving at a velocity in the fluid, and then the fluid has some viscosity, you have a drag force, okay, which is viscous force. Okay, so now you can find out the expression for the terminal velocity, and finally you substitute everything, okay, then you can know the terminal velocity. So I want to tell you that if eta increases, that means that the fluid is more viscous, okay, the fluid is more sticky, is stickier, okay, then the terminal velocity will decrease, so that the slower the ball will fall. Yeah, so that's the end of this video. Hopefully you can learn something from the series of videos here. Thank you.